3, and now we are going to see Chernoff bounds. This is a family of bounds. It's not just one bound, but a family of bounds. They are tied together by the technique, the way we derive these bounds. And an important concept along the way, we will try to understand the notion called moment generating functions. These moment generating functions, they are quite nice because they capture all the moments. If you recall the moments, the nth moment is expectation of x to the n. This one moment generating function is like a bag that just collects all of them together. So, if you recall, the Markov's inequality required the first moment, Chebyshev's required the second moment. Why is Chernoff so powerful? Because it includes information of all the moments. And as it turns out, if you have all the moments, you actually uniquely define the random variable. So, it's this moment generating function actually captures or characterizes random variables uniquely. So, that is why this is significantly more powerful than Chebyshev's inequality. And we will work out Chernoff bounds for the sum of some Poisson trials. It is basically a generalization of sum of Bernoulli trials, which is what we call binomial distribution. It is a slightly more general version for which we will work out the Chernoff bound. Okay. So, here is the Chernoff bound technique at a very, very high level. Okay. Let us set that in the backdrop of Chebyshev's. How did we prove Chebyshev's inequality? We took a random variable x. Okay. We asked what is x minus e of x, the probability of x minus e of x greater than or equal to a. Well, we did not know how to handle that, but we squared it. Okay. And when we squared it, if you recall, the event stays essentially the same, but now you are able to apply the second moment, right? And that is what we did for Chebyshev's. Okay. We are just going to push this further to the extent possible. What we are going to do is not square it, but take the exponential. Okay. So, now let us say you want the probability that x exceeds a certain quantity a. What we do is we pick a suitable t, which is some quantity greater than 0, okay? And we ask, when we say, we morph this this event over here, x greater than or equal to a, to e to the tx greater than or equal to e to the ta. So, basically we are exponentiating on both sides. So, the inequality stays the same. So, the event is really capturing the same thing. So, the two have equal probabilities. And so, you can easily see the analogy between this and Chebyshev's inequality. It is essentially the same idea, but here we are pushing into the limits, not just squaring it, we are exponentiating. And the nice thing here is now for the right tail, this is what we have here is the right tail, x. We were asking what is the probability that x exceeds some position a, some value a, and that is giving you the right end of the tail. For the left end of the tail, all you need to do is pick a t that is less than 0. Okay. And when you say pick a t that is less than 0, then you can ask what will happen. What you do instead of greater than or equal to is you say what is x, what is the probability of x less than or equal to a. So, that will be the left tail. And for that, remember your t is going to be less than 0. So, what will happen over here when you apply this inequality is how do you convert the less than or equal to a greater than or equal to, you will raise it to the power e to the tx in this context, but t being less than 0, your what happens over here is you will have a negative in the exponent. Okay. So, the inequality will appropriately fall into the greater than or equal, and which means that again you can apply Markov's inequality and so on and so forth, right. And that is exactly what we are doing here. So, for the moment let us not worry about the left tail, let us continue to focus on the right tail. So, if you what you can now do is apply the Markov's inequality. So, what we have is a random variable here, and we are asking what is the probability that it is more than some positive constant, and you will you can then apply Markov's inequality. So, you see how Markov's inequality is still the basis upon which all the other tail bounds are derived, but nevertheless we are able to do fancy things now. Okay. So, now we have to complete the story. So, we need a good bound for this numerator over here, the expectation of e to the t x, okay. And that is something we will focus our efforts on. Okay. But if we have the right bounds for the numerator, what we can do is we can play with the value of t. So, this is true for any t greater than 0, which means that for the best bounds you may need to play with choose the right value of t, okay. And then hopefully the terms will cancel out nicely and you will get a bound, that is a Chernoff bound. Basically this is a technique, a general technique to deriving these sort of bounds, and any bound derived using this general technique of taking the random variable, exponentiate and asking what is the probability that it exceeds a particular value, then taking the exponentiation on both sides of that event and applying Markov's inequality and bounding the numerator. So, this is a very standard technique. This technique is called the Chernoff bounds technique, and any bound derived from it is a Chernoff bound. Okay. So, just to recall, now we have to worry about this expectation of e to the t x. Okay. And as it turns out, that fits very nicely with a well known notion called the moment generating function. Okay. What is the moment generating function of a random variable x? It's exactly what we want. It is denoted mx, by the way this has to be a capital X. Mx of t is defined, this equal to the delta on top of it is defined as the expectation of e to the t x. Okay. This is exactly what we want, and we have a quantity, we have a well defined notion, okay, the moment generating function. Let us try to understand this object, this moment generating function. First theorem about the moment generating function, it captures all the moments. Okay. This is something that we talked about a little while ago, right, the Chernoff bounds. Why is it so powerful? It is capturing all the moments, not just the first and the second moment. So, why is that the case? And it is under some conditions. So, here the condition is that when we have expectation and differentiation, we should be able to interchange the way we apply them. Okay. If we can interchange them, then we have this theorem. Okay. So, basically what are we claiming here? This expectation of x to the n, this is the nth moment. You simply get that by taking the nth derivative of the moment generating function. This is the nth derivative of the moment generating function, then evaluate it at the position 0. Okay. Then you basically, by doing that, you get the nth moment of the random variable x. Okay. That is the nice thing. So, basically what is happening here is that the moment generating function in it's somehow capturing all the moments. When you as you take the derivatives, each derivative evaluated at 0 gives you the appropriate nth moment. Okay. Now, proof is quite simple. You look at the nth derivative of the moment generating function. Okay. And remember, this one important thing to notice is that you are taking the nth derivative not with respect to x, but with respect to t. Okay. So, dn by dt to the n. So, that is the nth derivative of well, what is the moment generating function? It is expectation of e to the t x, right. So, you apply that. And remember, we have said that differentiation and expectation can be interchanged. So, I am just interchanging it and taking the differentiation inside and taking the derivative. So, here derivative, the nth derivative of e to the t x is x to the n e to the t x. Okay. This is, remember, the derivative with respect to t. Okay. And now you, so now that you have this form, you can just start applying or evaluating this expression at t equal to 0. So, when you evaluate it at t equal to 0, essentially this term will vanish away, you will get e to the 0 x, and that is just a 1. Okay. So, you will just be left with e to the expectation of x to the n, and that is what we have over here. So, the nth derivative evaluated at 0 is expectation of x to the n, which is the nth one. Let us look at one more specific example where this is applied. Okay. So, now let us go back to our favorite Bernoulli random variable. We just want to confirm this. Basically, what are we doing here? We are taking the nth derivative, evaluating it at 0. We need to be able to get the moments. Okay. And let us just test it out for a very simple case. This is the simplest possible case that you can think of. So, what is the moment generating function? That is expectation of e to the t x. Okay. And that, what is this expectation of e to the t x? Well, essentially the random variable is e to the t x. What is the probability? I mean, with probability p, it is going to take the value e to the t, because x, remember this e to the t x is defined based on x, and x will be 1 with probability p and 0 with probability 1 minus p. Okay. When x is 1, you are going to get e to the t 1, which is just e to the t, that is, so you get p e to the t, plus when x is 0, you are going to get e to the 0, which is a 1. So, you, when that happens with probability 1 minus. So, that is how you get this expression for the moment generating function for and then you can play with it a little bit and apply the fact that 1 plus x is at most e to the x. Okay. And you can get it to be of the form e to the p times e to the t minus. But the most, for now, the form that we want is this, what is shown in yellow. Okay. So, now we have a moment generating function. Let us take the first derivative, and when we take the first derivative of this expression, this it is with respect to t. So, you will just be left with p e to the t, and when you evaluate it at t equal to 0, e to the t becomes a 1, and so you are left with p, and that is expectation of x. If you recall, this is fitting exactly the theorem that we have just proved. If you take the first derivative and apply it at value t equal to 0, you get back expectation of x. You can do the same thing with the second derivative. Okay. I will leave you to work that out on your own time. But essentially the second derivative, I mean the second moment is for the Bernoulli random variable is going to continue to be p, and you are going to get the same. So, the other thing is that not only does it capture all the moments, when it captures all the moments, it fully defines the random variable, and this we are just going to state the theorem and going to skip the proof. So, what is the theorem stating? If you have two random variables x and y, and if they are moment generating functions in the vicinity of 0, what does that mean? When t is around 0, it is between minus delta and delta. If both those moment generating functions are exactly equal, then we are guaranteed that both x and y are essentially the same distribution. Okay, essentially the same. Okay. So, this is this tells you once, I mean, if anything, this tells you that the moment generating function really gets to the heart of what a random variable is. Okay, really can characterize random variable. And one more nice theorem before we get back into Chernoff bounds. Okay, what is this? If you, this again is a way to exploit independence of random variables. Okay. So, you have two random variables x and y. X plus y itself is a random variable. So, there is this well defined notion of the moment generating function of x plus y, and that is this left hand side. Okay. The nice thing is that is just the product of the individual moment generating functions when x and y are independent. This is not true when x and y are not independent, but when they are independent, you have this. Okay. And this is very useful because later on when we are trying to bound say the binomial random variable or sum of Poisson random variables or whatever, you will exploit independence, and this is a key crucial requirement for that. Okay. So, why is it? Okay. So, you take the moment generating function for x plus y, you apply the formula, that is nothing but the expectation of e to the t times x plus y. Okay. and you expand it out, you get e to the t x times e to the y. But the nice thing is, now these are two random variables, e to the t x and e to the t y. If x and y are independent, then e to the t x and e to the t y are also independent. Okay? And if they are independent, the expectation of their product is the product of their expectations, and that is what we have over here, and that is by independent. Which, okay, what is each of these multiplicative terms? It is nothing but the moment generating function of x and the moment. Is this clear, what we have talked about so far? Any questions? Now we are ready to get back into the Chernoff bounds, and we will work out a particular example. It is basically the sum of Poisson trials. This is, if you recall, what is the binomial distribution? It is the sum of n Bernoulli trials. The sum of Poisson trials is just a generalization. It is just the techniques. So everything that we say from now on with respect to Poisson trials is going to be applicable to Bernoulli, the binomial distribution as well, but in fact it is going to be one step more general. Okay. What is the general part of it? When you take the binomial distribution, each Bernoulli trial must have the same probability of success p. Okay. When we go into sum of Poisson trials, we are generalizing, we are allowing each Poisson random variable xi to be 1 with some probability pi and 0 with some with probability 1 minus pi, and these pi's can be different for each xi. So, what is x equal to x1 plus x2 plus and so on up to xn? Each one can have its own probability of success. Okay. So, that is the general nature of sum of Poisson trials. So, of course, if all of these pi's are equal, you get back binomial distribution. Now that we have established that, so we know what the sum of Poisson trials is. It's essentially binomial distribution, generalized a little bit. Let us work out Chernoff bounds for this x, which is the sum of Poisson trials. Okay. So, we will need, remember, to apply the Chernoff technique, we will need e to the t x, which means that is we need the moment generating function. Okay. So, the nice thing now, we immediately start applying the theorem based on independence. Right. If you want the moment generating function for x, okay, it is basically the product, because these individual xi's are independent. The moment generating function for x is the product of the moment generating functions for the individual xi's. So, what is the moment generating function for the individual xi? If you recall, we worked this out a little while ago when we worked out the Bernoulli trial with respect to probability of success p. We worked it out to be of the form e to the pi times e to the t minus 1 a few slides ago. Okay. So, we are just applying that over. And so, now you have the product of several exponentials, which means you can take the e to the, you can take the exponential of their sum of their this product of the exponentials is just e to the sum of the okay. And what is that? This e to the t minus 1, and I think this needs to be slightly clarified. This, it looks like this e to the t minus 1 is in the subscript over here. It is actually pi times e to the t minus 1. This e to the t minus 1 can come out of the summation, because the summation is with respect to I. So, you get e to the t minus 1. If this comes out, you will be left with summation I pi. What is summation I pi? What is pi? Pi corresponds to random variable xi. Expectation of xi equal to pi. So, what is summation of over I pi's? Expectation of x, and we are going to denote that by mu. So, we have got the moment generating function, which means now we can go back to the Chernoff technique and apply this. So, let's before we start applying it, let me state the bounds that we can get. Only one bound I am going to prove, the rest of them you will have to prove on your own. I mean, the textbook has it, so you kind of have to take some time to work through them. Okay, the first, and if you recall, I said there is this one framework or technique, the Chernoff bounds technique, and you can derive multiple bounds. So that's why we're going to give multiple bounds now. Okay. Now the first bound, for any delta greater than 0, the probability that x exceeds 1 plus delta times mu. So just to give yourself a picture for what is going on here, you have a random variable x. This is e of x equal to mu. You have this some distribution, and you're asking, well, and let's say this point is 1 plus delta times mu. We are asking what is the probability that x will fall in this right tail, and that is at most this right hand side quantity, e to the delta divided by 1 plus delta raised to the 1 plus delta, the whole raised to the mu. Looks complicated, but there are nicer forms. This is why it helps to have multiple Chernoff bounds. So let us look at the second form. We have here, we need to restrict delta to be at most 1. What is probability x greater than 1 plus delta times mu? Again, this is the same story. You're basically trying to bound the right tail. It's e to the minus mu delta square by 3. Okay. Why? And you hope this might look like just some mathematical jargon, but let's pause for a moment to see why this is powerful. In the binomial distribution, what is your mu? Mu is the average, right? So if you have like 10,000 coin tosses, what is your mu? It's 5,000. And where does, in the tail bound probability, where does mu appear? Mu appears in the exponential, and it's e to the minus mu. Okay. So as the mean increases, the probability decreases exponentially. Okay. So that's the power of this Chernoff bounds. The probability of deviating from the expectation, this tail bound, it drops exponentially. So in that example, this coin flipping example that we have worked out in the past, it will show up as e to the minus 5,000 times delta square by 3. So these delta square and 3 are all relatively small quantities, but you can immediately see as the number of coin flips goes larger and larger, your probability of deviating significantly from the mean drops very, very quickly. Okay. So hopefully this intuition is making sense to you, because that's very, very important. This is what is telling you about the power of the Chernoff bound. Okay. And one more convenient form, which it is, well, it is positive for the numerator, it is positive also for the denominator, and if the denominator is dominating, then it's going to be again having the same. Okay, what's the third form? For some r greater than 6 mu. So basically this is useful when you want to ask what's the probability of deviating beyond 6 times expectation. In some cases this makes sense. Again, you see this exponential drop. Probability of x exceeding r is at most 2 raised to the minus r. Yes, so that makes sense, particularly for things like normal distribution and things like that. Here, so when you work with the standard deviation, you are actually working with Chebyshev's inequality or some related equality, and you can do that, and it's usually done because you don't have a handle on the moment generating function. What you're saying is particularly true for a lot of fields, but in computer science, often we define the algorithm, which means that we control what random variable, what the random variable is going to look like, which means that we have more power in our hands. We can go into Chernoff bounds, and that is what will happen very commonly. We end up being able to exploit Chernoff bounds because we have access to all the moments, and therefore, implicitly, we do not explicitly think about it all the time, implicitly we have access to all the moments, and so we will be applying the more powerful techniques. And this is significantly more powerful than just asking how many times away from how many standard deviations away from the mean you are. So, this is I think your question is also motivated by this, right. This is just one convenient form. It might be useful in some cases where the mean is small. If the mean is small, then you can ask what is the probability that you are exceeding 6 times the small mean, then it might be this might be a convenient bound to use. And again goes to say that it is basically the same technique. All these 3 bounds are derived using the same technique. It is just playing with the value of t. If you recall, there is a t, a parameter t showing up in the derivation of Chernoff bounds. Just playing with the value of t and other mathematical minor mathematical juggleries, you get these convenient forms. Okay. And so, when you think about applying them, you will just choose the most appropriate one, and typically the second form is the most commonly used form of this. Okay. And as I said, the same technique can also be applied in the left tail as well. Okay. We will see that, but for now let us actually look at the proof. So, just to be clear, all these 3 have the proofs in the textbook. I am only going to go through the first inequality, so that we have one inequality nailed down, we know how to do it, but the other things I still expect you to go through it on your own. Okay. Okay. So, we are now focusing on the first inequality, x is greater than 1 plus delta times mu, and here delta is any value, any positive value, and we need to prove that it is at most this right hand side. Okay. And again we are going to apply the exact Chernoff bounds technique that we have already seen before. We are just going to say what is x greater than probability that x is greater than 1 plus delta times mu. Well, you take the exponentiation on both sides, probability of e to the tx greater than e to the t times 1 plus delta times mu. This is standard technique. Apply the Markov's inequality. So, that is you get expectation of e to the tx divided by the right hand side of this event. Okay. So, but we already know this. We know, remember we just a few slides ago we derived the moment generating function for the random variable x, and that is nothing but e to the t minus 1 times mu. If you recall, we did that. Okay. So, I am just applying that over here. So, you get this form over here. Now comes the trick, because now you have to choose a particular value of t that will be convenient for you. Okay. And you see a lot of e to the t's, and if you want to cancel things out, what do? When you have e to the some ln of something, the e and the ln cancel each other out, right. So, that is what we are going to exploit. So, we are going to set t equal to ln 1 plus delta, and because delta is greater than 0, this ln 1 plus delta is also going to be greater than 0. So, which means we can apply it. So, going back to this form, if you apply t equal to ln 1 plus delta. So, essentially here you will be getting ln 1 plus delta. So, what will you get over here? You will get e to the t will become ln 1 plus delta. No, it will e to the ln 1 plus delta will become 1 plus delta minus 1. So, it will be 1 plus delta minus 1 divided, now I am going to take the whole to the mu separately, and here e to the t will become ln 1 plus delta. So, and this 1 plus delta will be plus delta over here, which is exactly the form that we. So, this is the first technique. The other techniques in similar fashion will be derived, and in fact, in this case you look at the other, you basically play with this form. This is one of the best forms that you can get. The other bounds are obtained by just playing with. So, those are left as homework for you. So, now let us Any questions before I move on and how this derivation works out? This is just two forms for the left tail that we have. Again, they look quite similar because their derivations are essentially of the same pattern. Now, because it is a left tail, you need to consider delta values to be in the range 0 to 1. And you have these two forms. Again, here it is x less than or equal to 1 minus delta times mu. So, you will essentially what you are doing is, if this is your mu, this is going to be your 1 minus delta times mu. So, you are asking what is the probability of this left tail. That is again at most some quantity, which is, if you notice, it looks very similar to the type of bounds that we have. And the second form is also there, probability x at most 1 minus delta is at most e to the minus mu delta square by 2, and usually this form is more useful. And in fact, you can take the two left and the right tail, the second form of them. This, in this case, it is this one. We had something similar in the right tail as well. We can put them both together and apply the union bound, and you can get a combination of both right and left tails. So, this is here because it is combination of right and left tails, you have the absolute value of x deviating from the expectation to be greater than some delta times mu is at most 2 e to the minus mu delta square by 3.
The type 1 previous slide.
What is the type?
Divided by 2 or 3?
It is divided by 2. It's this happens to not be a typo. But when you apply the union bound, you are just a little bit relaxed about how you apply it. The first one is I believe the tightest, but it really is not so much about tightness in these cases, because the tightness usually just gives you some, I mean typically the benefits are just in constants. You usually use the more appropriate question would be which one is the most convenient one to use. Of course, in some cases one might be convenient, but might not give you the good enough bound, right. So, the first one is usually the tightest, because it is pretty close to what you want. But what is also, and the reason why I even went through the proof of the Chernoff technique is that there are some cases where you actually have to redo the proof of the Chernoff technique for a specific t value that fits the application. Remember this, here we applied a particular t value that nicely cancel things out, and it is great for a general form, but there are applications for which you really have to go through the derivation and choose the appropriate t value and all that. So, it is good to know the general derivation technique. So, we are now almost done. Only thing I want to point out now is how this Chernoff bounds that we have seen so far fares with respect to coin flips. This is the example that we have seen. Here now we are going to ask what is the, so x is the number of heads out of n coin flips. Okay. So, this is essentially the binomial distribution, and since we know even how to handle Poisson sum of Poisson trials, we can actually handle the binomial distribution, which is just a special case. So, we want to ask what is the probability that so in the particular example that we had, n was 10,000. So, the mean would have been something like 5,000, right. And we are asking what is the probability that it deviates away from the mean by this quantity. Okay. And so, let's work that out. So, this is just this is recall, this is if you ignore the constants, essentially what you have is a square root of n ln n. Okay. So, it is basically if you for a rough understanding of what we are talking about here, what is the square root of 10,000? Well, it is roughly 100, right. So, we are asking what is the probability that x deviates from the mean by more than roughly 100. Okay. if you just ignore the constants in the ln term. Ln is small, constants are also small. Okay. And let us see, how do you work this out? So, here on the right hand side, you need it to be of the form delta times mu, right. So, you should work out the appropriate. So, we on the left what we have over here is what is exactly the tail bound that we want. We want to understand what are these tail probabilities. Okay. But now we have to fit it to the Chernoff bounds form. Okay. So, now what is your mu? Mu is n by 2. So, your delta, if mu is n by 2, what you have to do to get the mu to get the delta is just multiply by n over 2 and also multiply by 2 over n. If you do that, you get this will be your mu, this 1 n o. So, basically let me write that a little bit more carefully. Over here what you do is you multiply by n over 2 and you also multiply by 2 over n. Okay. This n over 2 is nothing but your mu. Whatever is left is your delta. Okay. So, so now we have all the delta and the mu. So, we can apply the formula, and if you recall the formula, it is 2 e to the minus mu delta square by 3. So, that is what you are applying over here. Okay. And when you apply, you get 2 over n. And for a similar range, what did we get out of Chebyshev's? I think we got something like 1 over 9 or something like that. The probability of exceeding 5000 plus or minus 160 we got was something like 1 over 9. But now what are we getting? We are getting 2 over n. So, this is like 2 over 10,000. Okay. So, you see how the tail probability is much tighter when you use the Chernoff bounds. Okay. So, that is generally the idea here. Wherever possible, you want to use the Chernoff bounds, but when it is not possible, you live with the Chebyshev's or the Markov's inequality. Okay. So, with that we can conclude our segment for today. So, we introduced the Chernoff bounds technique and you know, along the way we picked up an understanding of moment generating functions. We looked at some properties and we worked out the derivation of a Chernoff bound for the sum of Poisson trials, at least one form of it. There were other forms that we have stated, we have not actually looked at the derivations. Okay. And what we did was we applied it to the coin flips. Okay. And we saw it is immediate how powerful Chernoff is compared to Chebyshev's. I hope you can appreciate this difference. So, that is what we have seen so far, and in this module we have seen two slightly larger segments. So, we have seen the analysis of the median algorithm in the last segment, which is again a slightly longer module, and this Chernoff bounds technique, which again is slightly longer module, 5 segments in this module 3. Okay. So, in the next module what we are going to do is we are going to focus on applications. We are going to, now that we know all these bounds, these Markov's inequality, Chebyshev's and Chernoff's and things like that, what we are going to do is start looking at some algorithmic contexts, and we are going to start applying them. So, hopefully these bounds come alive to you. So, you will actually see how they help in computer science. Okay. So, that will be the topic for next module. Okay. Thanks.